Thank you all very much. Good morning. Thank you to Francesco, Ari, Alex, Tatiana, and Tiani for inviting me to speak and for putting together this wonderful workshop. I have to say, though, I was a little bit disturbed. I was reading the schedule, and if you read the schedule literally, then both the free afternoon tomorrow and the dinner at Queen's are going to be live streamed for YouTube. I wasn't planning on doing anything particularly wild at the dinner, but even so, that feels a little bit intrusive. So my goal today is to propose a quantitative notion of permutation stability. I'm going to try and convince you that it's reasonable. So this is for arbitrary finitely generated group gamma. So gamma will be finitely generated by a fixed generating set S of size D, and F is the free group on that same set S, and pi is the obvious epimorphism from the free group onto gamma, sending S to itself. And the question that sort of motivates this perspective on the study of stability is, given a homomorphism rho from the free group to a finite symmetric group of degree big N, so this takes some word in the free group and evaluates it at a d-tuple of permutations, sigma 1 up to sigma d, so it sends W to W of sigma. Can we test cheaply when rho factors through pi? So in other words, does this tuple of permutation sigma actually give us a not just a map from F, but a map from gamma? And the sort of naive test that you might do is just take some relations, take some things in the kernel of pi, evaluate them at sigma, and try to see if you get the identity or not. So pick some finite subset of the kernel of pi in some way, and for each word, each relator R in this finite subset of relators E, pick some points in the domain of the permutation, uniformly at random with replacement, and compute where the point X is sent by the permutation R of sigma. Okay, and I'm going to assume that testing a single permutation in my tuple sigma at a single point X is an operation that has some constant cost. So that's just evaluating, so maybe there's some oracle that does this for you. You press one of the buttons marked sigma 1 up to sigma d, and you press the button marked the point X, and it tells you the output. So testing a finite set of elements each at k random points is going to have a total cost of k times what I'll write as the norm of E, where this is just the sum of the lengths of the elements in the set E. Right, because if testing one permutation in sigma at one point has constant cost, then testing a relator R at one point under sigma is going to have cost proportional to the length of that relator.
What is R?
R is an element of my finite set E, which is a subset of the kernel of pi. Okay. And of course, we hope and expect that all these things are trivial, so they should fix every point. If that doesn't happen, then we recognize that rho does not factor through pi. And in that case, we say that the test that we've run has been failed. If the test is passed, then can we conclude that rho does factor through pi? Well, not quite. What we can conclude instead is that with high probability, we have the following conclusion. That this is conclusion star, that the supports of the rho of the R of sigma are small, namely that they're at most delta n for all relators R in the set E, and this is for delta approximately 1 over k. So when I say high probability, I mean, I suppose, 50% probability, 90% probability, 99% probability. So the point is, if this has large supports, then with high probability, picking points x at random after k iterations, I am going to find a point x just by chance at which one of my relators doesn't fix that point. So if I fail to do that when with high probability, the supports are small. Okay, then this brings us to the definition of stability, which we saw yesterday. We say that the group is permutation stable, although today I will just say stable, if for all epsilon greater than 0, there exists a delta greater than 0, and a finite set E in the kernel of pi. Such that for all positive integers n and for all homomorphisms rho from the free group to sim n, if we run the test and we conclude correctly that the supports of the words in E are small, then rho is close to a genuine homomorphism from gamma. And in some sense, close to a genuine homomorphism is the best that we can do so cheaply. Because, of course, there could be imposter homomorphisms, rho, which do not factor through pi, but they've been obtained by taking something that does factor through pi and just randomly perturbing it at a few points, breaking it at a few points, so it fails to factor. This test will never detect such things because at most points they look the same as a genuine homomorphism. So those will slip past the test. But stability is saying that that's the only thing that can go wrong. Okay, and the cost associated to running this test motivates my definition of quantitative stability.
May I bother you about the E? There exists E or for every E?
Yes, sorry, for all epsilon and there exists a delta and there exists an E, finite. So there is some E that you can use to run the test on.
Even if the group is not finitely presented.
Indeed. I really want this definition to be valid for non-finitely presented.
What we usually use is
I'm going to address that in a moment, but I don't know, but probably not. By what we usually use, you mean stability rate.
What?
By what we usually use, you mean stability rate for a finite presentation.
Stability that, you have an infinite sequence and
So qualitatively the same, quantitatively I'll say something about that in a moment. So in my definition, the stability growth function which I need to find a better letter for. At the moment I'm just calling it capital F. So this is the stability growth function of gamma depending on the generating set S, although the dependence is not very strong. And this takes a positive number, outputs a positive number, and it's given by, so it takes in an input x, which I then immediately write as 1 over epsilon. So that will be the epsilon in the definition of stability. And this is sent to the infemal value of the norm of E over delta as E and delta range over all pairs of a finite set and a positive number delta satisfying definition 1. Right, so this function grows slowly if there is a way of running this test cheaply. If there is some finite set E such that you only need to test that set at a, the set is quite small and you only need to test it at a sort of moderately sized parameter delta, and that this will tell you what you want to know. Okay, so Alex asked about finitely presented groups. So in that case, stability can be equivalently characterized in a different way, where you say, so in a finitely presented group, of course, the kernel is finitely generated as a normal subgroup. So in particular, there is a finite subset R of the kernel that generates it as a normal subgroup. And it turns out in that setting, in the definition of stability, you can always take that finite set R to be your E. So let me make this as a remark. So if gamma is finitely presented, then we can always take the set E to be the relation set R in the definition of stability.
Because you care about this function only up to constants.
Yes, yes. Yeah, exactly. So I'm talking about a function here, but of course really mean I need an equivalence class of functions. Now, well, okay. For this, it's actually potentially something worse, I think, or at least I don't know that it's equivalent. So qualitatively, you get the same class of groups among finitely presented groups if you insist that E is equal to R, always. However, quantitatively, you could get a different notion, you could have a different runtime for your test if you insist that you only ever test on the relation set R. So this notion, where you fix E to be R and try to quantify stability, is already in the literature. So this is studied by my erstwhile colleague Oren Becker and Jonathan Mashayev. So they introduce a notion of stability rate for a finite presentation. And they don't quite express it this way, but it's essentially what I said. You are running the test to quantify definition 1, but with respect to the fixed relation set R, always. Now, this means that the stability growth function is always at least as small as the corresponding thing where you always insist that E is equal to R, because it might be that by varying the relation set in some clever way, varying the set E, a priori you have some more efficient way of running the test than if you insist that the relation set is the same quantitatively.
You have such an example?
I do not. The best I can say in the other direction is that you have a bound involving the Dane function of the finally presented group you're working with. But that is at least good enough to say the following. So this is taking those observations in hand and combining with the main result of Oren and Jonathan's paper. So they studied in particular the stability rate for finitely generated abelian groups, and a corollary of their main result is that for each d equals greater than or equal to 2, the stability growth rate of z to the d can be bounded above by some polynomial function of the argument depending only on the rank, and bounded below by so they gave an explicit lower bound, so it's either 1 or d minus 2 in the degree in the lower bound, whichever is bigger. For their notion of stability rate, they proved x to the d in the lower bound, where d is the rank. The minus 2 comes from the fact that the Dane function of z to the d is quadratic.
Can you bring this down?
Oh, thank you. Okay. Any questions so far? Okay.
Sorry, so
Yeah.
you're saying that the relation between their quantitative notion and your quantitative notion in this case, so theirs is with x to the d and yours is with x to the d minus 2?
Yeah.
But that's just like a rough estimate. It could be the same.
Yeah, so they don't claim in their paper that their estimates are sharp. They show that there is an upper bound depending on d and a lower bound depending on p. Alan?
So for z squared, we don't know whether this function is unbounded. Like it might be constant.
So that's why I have the maths here. So just as for the stability rate,
It's at least linear.
it's at least linear unless it's the trivial presentation of the free group. Okay, so how might you bound the stability growth rate? Well, kind of one of the key motivations for studying permutation stability, which was talked about yesterday, is that it presents us with a potential pathway to finding a non-Sophic group. So, so this is the kind of the basic slogan. If you're Sophic and you're, I'll leave some gaps here. If you're Sophic and you're stable, then you are residually finite, which I will always say as RF for short. So, so the strategy is produce a group which is stable, but which is not residually finite, then you found yourself a non-Sophic group. And variants of this strategy have been employed successfully to construct groups that are non-approximable in fashions analogous to non-sophicity in other contexts, but we haven't been able to apply the strategy to find a non-Sophic group yet. So if one kind of believes this, follows this philosophy, then it seems reasonable that there should be a quantitative version of this observation, namely that if in some sense you are very Sophic and very stable, then you should also be very residually finite. So, such that if your goal more modestly was not to construct a non-Sophic group, but just to construct a group that was not very Sophic, that was sort of on its way to being non-Sophic but not quite there yet, then you also have a strategy, namely you have to construct a group that is very stable and not very residually finite, whatever that means. Now that's all fine in principle. I have failed to implement this strategy so far. Because, I mean, proving groups are stable is already hard enough. Proving they are very stable is even harder. However, we do have ways of proving groups are not very residually finite. That's something we can do. So what I have been able to do is use this strategy in another way by saying if you have a group that is very Sophic but not very residually finite, then you conclude it is not very stable. Now, in and of itself, that's not interesting at all because your group might fail to be stable altogether. But if it is stable, then I think you've proved something interesting there. And that is the main result, which I'm hoping to put up on archive at the end of term. So I'll state it like this for now because I want to refer to the same class of groups several times in several different results. So there exists a class of groups, C, of two generated residually finite stable groups to be described such that for all non-decreasing functions f, there exists a group gamma in my class C whose stability growth function dominates f. So the stability growth function can be as fast as you like while still remaining finite, while the group still remains stable. I should say, so my particular choice of stability growth function, I mean, so stability, the cost of running the test depends on these two parameters. It depends on this parameter delta, and it also depends on this finite set E. In making this definition, I've made a choice about how to weight those two parameters. I said the cost should be, you know, the norm of the finite set E times by 1 over delta. And I've motivated that choice by referring to this test, that the cost of running this test should be about delta times the norm of E. Other notions of quantitative stability are available where you weight these two quantities in different ways. There is a lot of flexibility here. And this result would remain true for essentially whichever notion of quantitative stability you picked. The only stipulation I have is that that choosing longer words to test should impose at least some cost on you. So that the length of the words should matter at least somewhat in your definition. Alan?
Can I ignore delta completely?
You can ignore delta completely. So if you care about stability radius, then this will still work. All right, so I talked informally about very Sophic and very residually finite. I've defined what very stable should mean. It means that the stability growth function is full. It's more, I should define now rigorously what very residually finite and very Sophic mean. So the first of these by the way, how far down can I go here? Is halfway okay? It's maybe a bit iffy at the front. Okay, I'll try not to use very much of this board. So, quantitative notion of residual finiteness was studied extensively by Khaled Bourabeh and his collaborators. And the version that's most relevant to me was introduced in a paper of his together with Ben McReynolds. And this is the so-called full residual finiteness growth. Of a group gamma. And this is defined to be, so this is written in curly R. I'll move the board up in a minute. And this takes a natural number n to the smallest order of a finite group Q, such that there exists a homomorphism phi from gamma to Q, for which the restriction of phi to the ball of radius n in the word metric on gamma with respect to my generating set S is injective. With this restriction 1-to-1. Thank you. Right, so a group, so qualitatively you can take this to be a definition of residual finiteness. A group is residually finite if and only if for every finite subset of the group there is some finite group and a homomorphism from your group to that finite group whose restriction to that finite subset is injective. In a finitely generated group, our prototypical finite sets are the balls in the word metric, and so this notion is measuring how big the finite group needs to be for you to have injectivity on the ball. Okay, so we need a supply of groups which are not very residually finite. And we have one. So groups which are not very residually finite, i.e. very not residually finite while still being residually finite, were first constructed by Bradford together with Brandon Seward in a 2013 paper, which is actually still one of my all-time favorite papers. It's a lovely, clear-sighted piece of writing. So I took their construction and ran with it in a paper now published, appeared on the archive last year. I'm going to say for all functions f, so in general I would summarize this theorem as saying for all functions which are sufficiently fast and nice. That's rather informal. For example, which is more precise but a little harder to pass, if there exists a positive constant c such that the function f satisfies f to the f of n to the power n is bounded above by f of cn for all n. That would be sufficient for the function to be sufficiently fast and nice in my sense, which roughly speaking says this grows at least like e to the n to the log n and doesn't oscillate too much. So that's sort of my how fast I need it to be. You can get weaker statements than what I'm about to write for slower growth functions as well. So for such functions, there exists a group gamma in my class C, the same class as in theorem A, such that the full residual finiteness growth is equivalent to the function f. And as I said, that the full residual finiteness growth dominates the function f. This is essentially due to Bradford and Seward 2013. I'm not going to promise that the groups they construct are exactly in the class C as I am going to define it, but they are very close relatives of groups in the class C. It's essentially the same construction. So my work was to find a matching upper bound. Today, it's actually the lower bound we care most about, because I want these groups to have large full residual finiteness growth. I also need a notion of very sophic, and the notion I'm going to work with is due to Gulnara, together with Pierre-Alain Chéry. So their paper appeared on the archive in 2020. And so they defined the Sophic profile of a group gamma, kind of in an analogous way to the full residual fineness growth, but sophicity is not defined in terms of homomorphisms defined in groups, it's defined in terms of almost homomorphisms. So what does this function do? It takes n to the minimal degree of a symmetric group, so capital N, such that there is a 1 over n Sophic representation from the ball of radius n to ball of radius n in gamma to sim n. So by 1 over n Sophic representation, I mean it is 1 over n multiplicative and it is 1 minus 1 over n separating in the Hamming metric.
Can you remind what is the definition of 1 over n Sophic approximation? If it is finitely presented, I guess I know.
So I mean, so this is a function at the level of the group gamma.
Oh, sorry, yeah, it's only on
Yeah.
the ball.
Yeah, exactly. So this is actually defined on gamma, but it's not a homomorphism. Sorry? Okay, and so I said informally that very Sophic plus very stable should imply very residually finite. We now know formally how to quantify stability, sophicity, and residual finiteness. So I will turn this philosophy into a more precise proposition. So for pi, my standard epimorphism from the free group onto gamma, if the kernel of pi is non-trivial, in other words, if I don't just have gamma is the free group and its generating set is the standard basis, then we have the following functional inequality. So if you take the Sophic profile and you plug into it the safety, I'm going to say 2 times the stability growth at 2n, again just for safety, and then you take the factorial of all that, this is at least the residual fineness growth for all n. And the proof of this is really just the proof that Sophic plus stable implies residual finite. If you have a Sophic representation, this gives you something to which you can apply stability. That will give you an actual action on the finite set that separates points, and that gives you a small quotient in which the ball is mapped injectively. And so you just take that proof and you keep track of all the parameters. Okay. And so then the third result, I need the groups in this class C to be very Sophic. I'm not sure this really deserves the status of a theorem. It's not very hard. And I think there are probably various ways of proving this. I did it by constructing local embeddings of my groups into finite groups, so partially defined homomorphisms that don't extend to globally defined homomorphisms. But in any case, the conclusion is that for all the groups in my class, there's a uniform bound on the Sophic profile which is pretty slow, I would say. It's exponential in n squared log n. Maybe perhaps not very slow, but I mean, given that the Sophic profile can't be that much slower than the word growth, this is not too far off exponential. I will just make a remark, perhaps I won't write this down. So it was pointed out to me some years ago by Andreas that actually if you fix the size of the generating set, then there is a universal upper bound on the Sophic profile of every Sophic group on a generating set of that size. So for each d, there's some universal function fd such that if my set S has size almost d, the Sophic profile of gamma with respect to S is bounded above by fd. We don't know really anything, I think, about that, about what that function might be. So Gulnara is the expert on this, but I am not aware of groups for which we know the Sophic profile is, say, much faster than exponential. Is that still the state of affairs? Yeah, okay. There is a sort of much weaker general bound than this, which would actually do for the sake of the proof of theorem A, but I wanted to state this because it's quite nice and quite concrete. So in the time
So in a sense, every Sophic group is very Sophic, is what you're saying.
If you consider being bounded above by this function fd to be very Sophic, then every Sophic group is very Sophic. Okay. We hope and expect that this function fd is necessarily very, very big, but we don't know yet. Right, what I should do now is tell you what the groups in my class C are. Are there any other questions before I do that? Henry at the back?
Why you hope that I mean, why do you care? I mean, I was interested by the word hope.
Oh, well, I hope and believe that there are non-Sophic groups, and having groups for which I know the Sophic profile is big, irrespective of whether I independently know those groups are actually Sophic, would seem to be a step in that direction. I mean, put it like this: if I knew what this function fd was, then I only know that I only have to beat that function fd to produce a non-Sophic group. That may not be a good strategy, but it would at least be. It is at least something.
Yeah. Right. Sorry. Yeah. So sorry. The Sophic profile only makes sense for a Sophic group, right?
It's infinite if the group is Sophic,
so
but
is it not the case that if there was a smaller universal lower bound on the Sophic profile, it would be easier to prove the group is non-Sophic?
Indeed. So yes, but the thing that would force fd to be bigger is having a Sophic group of large Sophic profile, which is also my hope.
Okay.
So, what are the groups in class C? So they are groups that I have taken to calling generalized BH Neumann groups, and they are a very diverse family that I enjoy thinking about. They're constructed as follows. So you take a function d from natural numbers to odd natural numbers at least 5. Take an increasing such function. And sets g of d to be the product, the direct product of alternating groups of degrees dn. And I will pick two elements from this direct product. So I have a sequence alpha, whose nth term alpha n is just the standard n cycle of length dn, and beta sub n and Rn, where Rn is some other sequence that I will say more about in a moment. This is a 3-cycle with support 1, 1 plus Rn, and 1 plus 2 Rn. So these are elements of my alternating group. And, okay, I want these all to be, well, I want this to be less than Dn, so let's say Rn is less than Dn over 2. And I define my generalized BH-Neumann group, depending on these two functions d and r, so gamma of dr is just defined to be the subgroup of GD generated by the two sequences alpha and beta. So this is a subgroup of a direct product of finite groups. So immediately from that we see that it is residually finite. So the subclass of these groups that were studied by BH-Neumann, so the original BH-Neumann groups, was the subclass for which the function r is identically 1. Namely, the 3 cycle is just the standard 3 cycle 1, 2, 3. And Neumann was interested in these groups because they gave the, I think, first example of a continuous family of infinite finitely generated groups. So the original groups gamma d1 are pairwise non-isomorphic. So if you take different functions, you get a different group up to isomorphism.
Sorry, gamma d1 means beta is always 1 to 3?
Yes, so r equals to 1 means that Rn is identically equal to 1, so 1 plus Rn is 2, 1 plus 2 Rn is 3. Yes, I can count. The relevance of these groups to permutation stability was noted first in a paper of Ari Levit and Alex Lobotsky. Appeared on the archive in 2019. So they proved that all of Neuman's original groups are permutation stable. Okay, so now I can tell you what my class C is, and it is, it's not all of the generalized BH-Neumann groups, but it's a subclass on which I've imposed some extra hypotheses to make proofs easier, and which is still sufficiently flexible to do everything I want. So I take class C, which appears in all the theorems, to be those groups gamma dr, such that the following 3 things hold. First, D takes only prime values. R is strictly increasing. And Rn is at most dn over 3 for all n. Right. And for those groups, we have all of the properties that I described in the 3 theorems. So the Sophic profile is controlled. There are examples where the residual fineness growth is very big. And hence, the stability growth function is also very big. So all that is fine and not too difficult. The real work is in checking that the stability growth function is finite in the first place. So I actually want these groups to be stable. So what I need to prove, given the bounds on residual fineness growth and Sophic profile, and the proposition relating these to the stability growth rate. Theorem A, that there is a class of residually finite stable groups. Well, I require the groups to be stable. Okay, I will mention in connection with this result, before I say a few words about the proof and then finish, that of course this workshop is not just about permutation stability, there are other flavors of stability, and quantitative Hilbert-Schmidt stability was already studied by Alon, Ari, and Itamar Viktorovich. And in their paper they proved that this is not stating their result in the most general way, but a consequence of their result is that they proved that all of my groups in the class C and the original Neumann groups, gamma D1, are Hilbert-Schmidt stable. And as a corollary to this, given that these groups have large full residual fineness growth and bounded or uniformly controlled Sophic profile, therefore uniformly controlled hyperlinear profile, that you can conclude there are groups of arbitrarily large Hilbert-Schmidt stability growth. So these three authors in their paper don't state this this consequence in the most general form possible. So indeed, they only talk about what they call the Hilbert-Schmidt stability radius, which is, as per Alon's question, the version of quantifying Hilbert-Schmidt stability where you only care about the length of the words you're testing at. You don't care about the parameter delta at all. But just as my notion of stability growth for almost actions on permutation groups is very flexible. We can weight the two parameters, the size of the set and the parameter delta, in whatever way we like, just so long as we care somewhat about the word length. The same proof would also work in the Hilbert-Schmidt set. And so they actually get a result for any, I would say, reasonable notion of stability growth rate via essentially the same method. Okay, I think I'm not going to write anymore. I'm going to, okay, a few words about the proof. This is, so the group one, maybe I'll write one more thing. So a very useful lemma for understanding the groups in the class C is that they decompose in the following way. So they all fit into a short exact sequence. So gamma D are in the middle. On the left we have the direct sum of all the alternating groups in our sequence. So it is not obvious but true that the whole direct sum of the alternating groups lives inside this very thin subgroup gamma inside the direct product of the alternating groups. And what is the corresponding quotient? It is the Lamplighter group with lamps in C3. roughly speaking, the reason for this is because of the way I chose my function R in the definition of C. Points in the support of the 3-cycle get further and further apart as you go down the sequence. So if you look locally at your Cayley graph, what it looks like you're seeing is lots of elements of order 3 that commute with each other locally. And so this starts to look more and more like a Reith product. And a big part of the motivation for forcing D only to take prime values is that if you have a permutation group of prime degree, it's very easy to prove that it contains the alternating group, which helps me get the whole direct sum here. In particular, all of these groups, gamma D, are amenable groups. And for amenable groups, we have a now fairly standard pathway to proving permutation stability, thanks to Alex, Oren, and Andreas, which is to study their invariant random subgroups. Now, I'm out of time, so I'm not going to give an introduction to invariant random subgroups in -1 minute for people who have not thought about them before. If you know, you know. In closing, I will just say maybe a couple of skeptical words about my definition of quantitative stability. So, so one thing you might say is, well, certainly if the stability growth function is very fast, then we should consider our group to be not very stable, because any way that we might run the test to run the algorithm to test stability is going to be very slow, no matter which finite set E we choose. But the stability growth function being slow, does that really mean that we should think of the group as being very stable? I mean, that would tell us that there exists a small finite set in a moderately sized parameter delta that we could test on, but that's not very useful if we don't have any way of finding the finite set E. So it could be that there is a small finite set E to test on, but we have no way of obtaining it, and so we would just have to test blindly lots and lots of words, which might be very expensive. So possibly you should consider a stronger notion of quantitative stability where you insist not only that you have a small finite set E, but that you have some algorithm that will give it to you, given a parameter epsilon. So that might be a reasonable criticism. The other thing to say is you might say, well, okay, I've looked at one particular algorithm for testing these relations, these permutations, and that algorithm may perform quickly or not. But you might say, okay, maybe this algorithm was a bad algorithm and there's a better one. So you could sort of introduce a notion of quantitative testability where you say, it's not just one algorithm we care about whether there exists an algorithm that has good runtime for this problem. It turns out, thanks to work of Alex Slobotsky, Jonathan Mishayev, and Oren Becker, that every amenable group qualitatively is testable in some sense. There is some algorithm that works. And in fact, there is a universal algorithm that always works called the local statistics matcher algorithm. I believe, but haven't been able to prove yet, that the local statistics matcher algorithm yields uniformly good performance on all of my groups. They are quantitatively very testable in that sense. That is what I think happens, but I haven't been able to prove it yet. So I'll end with that as a question. Beyond constructing stable groups that are not very stable, can you construct testable groups that are not very testable? I'll stop here. Thank you very much.
Any questions?
Francesco?
Is there a scheme like this with stable instead of testable? And what do you put on the right-hand side?
With testable instead of stable?
Yeah. And can you say anything?
That's a good question. I haven't thought about that. I mean, certainly you can't say residually finite here because every amenable group is testable and there are amenable groups that are not residually finite. But yes, I'm not sure what you would try and find obstructions to get obstructions to efficient testability. That is a good question. Alex?
Can you say something about the stable rate if we want to restrict ourselves only to finitely presented groups?
So you mean the stability growth in the sense that I defined it for?
For example.
Or can I get obstructions within the class of finitely presented groups? I know no way of doing that, no. The groups in the class C are very much not finitely presented, any of them.
Basically, do we know some finitely presented groups that this is very large, except for the work of Becker and Mosiah on building groups? Do we know anything about it?
I had some conversations with Oren about this while he was here, and we tried and failed to find even a single finitely presented group which is not polynomially stable in either sense. So that would be the first thing to try to do for finitely presented groups.
That can happen, that every finitely presented.
It's definitely not true, but we couldn't provide the counterexample.
Do you expect do you expect a single finitely presented group of, like, for every function you have a finitely, like, that you don't have a gap?
So should this lower bound actually be an equivalence?
Yeah, like, do you have such a theorem in the context of stability rate for finitely presented groups? Incredibly many, so not enough functions.
Yeah. So I think in finitely presented groups, I would expect them to include very big things, but to be kind of sparse in some sense. Maybe computable.
Other questions? Then we have 8 minutes break.